Hello everybody, I'm going to talk right now about chemical kinetics, namely how concentration affects rate of reaction. So this is on roughly page 5 of your unworked out note set. So we're going to take the simple case of one reactant species, I'm just going to call it A, going to products. And we have what's called the rate law. This is called the rate law. The rate law, I'm just using R to represent the rate of reaction. We have the concentration of A, typically in molarity. It doesn't have to be. You could actually do this sometimes with partial pressures or different units of concentration, but we'll focus on molarity. And we have also what's called the rate constant. It's basically a proportionality constant. You can think of it like that. And this is called the order or the order of reaction. I'm just going to call it the order. And it's going to be typically N is going to be almost always, for our purposes, 0, 1, or 2. There are exceedingly rare cases where N is equal to 3, and occasionally N with certain types of reactions like radical reactions or half integers like 1/2 notably. We will not focus on that. We'll take the case that exists 99% of the time or more, and that's N is equal to 0, 1, or 2. So let's do a physical example of how this looks, how a typical rate law looks from simplified data. So let's take the case similar to what's in the notes, where we have the concentration of A in molarity. And the best way to do this is really to measure the initial rates. And I would probably do an instantaneous or near instantaneous measurement of initial rates to get this. So we'll have the concentration of A for different trials in molarity, and then we'll have different initial rates. And we're going to put the initial rates in just arbitrarily molarity per second, but it will allow us to do calculations. So this is molar concentration per unit time, and I'm choosing seconds. It does not have to be seconds, but that's what it is for this particular problem. So we got 0.10. These are different trials. You're starting off, this would be like trial 1, where you start off at 0.10 molar concentration. Trial 2, you're starting off at 0.20 molar. And trial 3, you're starting off at 0.40 molar. And what you're noticing that the initial rate with these different initial trial concentrations of species A, for this made-up example, we get these three values that I'm using as an example for the rate. If you notice, for different trials, when we doubled the rate, when we double the concentration, we went from 0.1 to 0.2, 0.2 to 0.4. With this example, very cleanly, it's a made-up example, we had doubled the rate each one of those cases. In that case, there's direct proportionality between the rate and the concentration. Rate is equal to Ka. You don't write the N in there, 1 in there, but that's the case where N is equal to 1. This is a first order reaction. We say it's first order. So that's a very common type of motif of reaction. We call it a first order reaction. And let's look at the units here. The units are important. If this is in your units of molarity per second, and then we got K, and we got units of molarity here, the units of K have to be 1/2 to make the units on the left match the units on the right. So with first order processes, the units of the rate constant are always 1/time. It doesn't have to be seconds, it could be minutes, hours, days, but it will have to make the left and the right side match each other, and so it will have to have an inverse unit of time. And so also one thing you can figure out, now this is contrived data, it's made up, so all the numbers work cleanly. Normally you would do this statistically, is we could actually, from this data set, calculate K. So you could take any trial you like. Let's take trial 1. So in trial 1, you have, just using trial 1, 0.015 molarity per second. This is the rate law. Rate equals Ka. And then we have that's equal to K. And then we're going to have the concentration A in that particular trial is, let's see here, that's going to be 0.10 molar. So when you do this out, just divide, and K is going to be what? It's going to be 0.15 inverse seconds. And because, again, this is I'll put this like this, or you could write it as 1 over seconds, however you care to write it. You could do all these trials, you get the same number. In real experiments, you would do it across the different trials and get the average, because this is contrived data to teach something, but in real life, you're never going to get something so clean as this. So this is an example of a first order reaction. We're showing how to get the rate constant, go through the other cases, verify it's that number. So let's take another case. So we have our general form of the rate is equal to Ka, the concentration raised to the order n. And then you look at the data. This would be on page 6 of the notes if you're working along. So let's say we have concentration of A in molarity for 3 trials. So we started off with initial concentration of 0.10, 0.20 molar, and 0.40 for these 3 trials, trial 1, trial 2, and trial 3. We're again dealing with the reaction A going to products. Not worried about the chemical details of it, we just want to get the idea of the math. And then let's say here's the initial rate again. R, let's just make it molarity per second. So the initial rate, which we denote as the symbol R, 0.015, 0.015. In this ideal setup, it didn't change. We doubled the concentrations for different trials, and then we could have more and more trials, keep trying this. And in this contrived example, we're seeing exactly the same rate, the same exact initial rate of reaction. So that means that the rate is constant. Rate is equal to K, which that means any number except for 0 raised to the 0 as unity is 1. So A to the 0 is equal to 1. So that means this is a 0th, put it a little higher, like a superscript. This is a 0th order or 0 order reaction. And these are very common. These exist, for example, in surface chemistry. These are not unheard of. They're one of the 3 pretty common motifs. I'd say the first order is probably the most common. Then 0th and 2nd are pretty common as well. So that's an example of a 0th order reaction. Oh, before we go on, let's just do an example how to get the rate constant out of this. So these would be the trials 1, 2, and 3. So we can take any trial. So all we have to do, there's nothing to do here, is that the rate is equal to K. So the rate here was very nicely, because again, it's a contrived example, 0.015, and there's no big calculation to do here. The rate and K are equal, they have to have the same units. So if the rate, the initial rate's concentration is concentration in molarity over seconds, then that's going to be the units of the rate constant as well. And so that's actually really easy, and a lot of people get this wrong. I do not know why. They say there's no units to it, but the units of a 0th order rate constant will be the same the same units as the rate constant itself. As the rate of the reaction itself. So that's actually pretty easy, but people for some reason tend to get it wrong. Not sure why. So let's take another case. I'll just erase here the rates. We do a similar experiment with another chemical system. We'll just call it A because we have a common name. We had 0.015. So when you have 0.10 molar of the concentration of A, we had 0.015 molar per second rate, and then it goes up. When we double the concentration, it goes up fourfold, and we double it again, it goes up another fourfold. It's going up as the square of concentration. So that means rate is equal to Ka squared. This is N is equal to 2. This is called a second order. I'm bad with my superscripts. A second order reaction. And the order is 2, and so we could write the rate law just as such. That's the rate law for a second order reaction. And we can figure out, let's talk about the units. What's going to be the units here? So if the rate's in molarity per second, we got molarity squared, because A squared. Do the math. That divide out. It's not really equal. This is giving the units, but I'll just use the equality sign. So it's going to be inverse molarity inverse seconds, and you can write it like that, or you could write it as having units of molarity raised to -1 second -1. That's another convention. I use both depending on how much space I would like to use, and do the same method before. Pick a trial, pick a concentration, square it, and show me that, let's see here, I got K is equal to 1.5, and I'll write it like inverse molarity, inverse seconds like that. Verify that is true using any trial. They'll all give you similar answers, because again, this is a made up example. So the with idealized numbers. So the big three cases you're going to have is rate equals K, the rate of reaction A. This is a first order reaction. You're going to have rate is equal to K, 0th order, and we have rate is equal to K with A squared, second order in A. So we have first, 0th, and second order. Those are the type of cases. Now we did a simplified case with just one reactant A. We're going to do something next with more than one reactant species, kind of generalize this, and then we'll move on to arguably the most important part of kinetics and the important part of exams, important parts of standardized tests like MCATs and GREs, is integrated rate laws. That will be coming up in a lecture or two from here. So we're getting into some pretty good stuff. Work the skill builders, rework these problems, see if I made any mistakes mathematically. It's possible. And also move through the skill builder work set and so on, and keep trucking along. Okay, on that note, take care.